Welcome back to 912, guys, and we have something called Green's theorem. So in the past, what did we do? We found the work done on an object moving from one position to another position where the path is given. And so it has to be smooth curve or piecewise smooth. And we showed this, it's C1 plus C2 for whatever it is. And we were able to find the work done on an object moving from one point to another point if the path is given. And then we did what? We found the work done on an object when it's independent of the path. So we were focusing on finding the work done. Then all of a sudden we jumped to double integration. What did we do in the double integrations in 910 and 911? We did 910. How do you integrate double? When the region is what? Type 1 or type 2. And this would give us the volume of the solid. In 911, we found also the volume if the base is what? Is polar region. So we did it with polar. Why did we do that? Because we're going to need it in 912 and 913 and 914, 15 and 16. What's in 912? What are we going to do today? Again, we are going to go back to finding what? The work on an object moving from one point to another, but the only difference today is that the path we are taking is a closed path. So you're going to start from Mississauga, you're going to go all the way to Toronto and come back again to Mississauga. I need to find the work done of delivering object going through this path and coming back to what? To your starting position. If you have a closed path, then you have to know that the integral can be easily done using what? Green's function. That's the key of this section, guys. All right, so if the path is closed, look at this one. This is a closed path, as you see. No matter where you start with, okay, no matter what you start with, the path is closed. So you can start from this point, for example, deliver, go all the way and come back to here. So this will make it what? Closed path. This is also a closed path, and this is a closed path. This is counterclockwise, positive direction, and this is the negative direction. So if you're going this way, this is a negative direction. Doesn't matter what the direction is, because we are going to use Green's theorem. What does Green's theorem say? It says if you need to find the work done, which is, by the way, the integration of f dot dr, which is p dx plus q dy, if you remember. But the difference here is that you see there is this sign, which means what? Closed curve. What do you do this? You don't have to go through all of this and going through the path at all. So what do? We are going to use dq over dx minus dp over dy. So we'll differentiate p with respect to y and q with respect to x. Start with it, subtract, you get this inside. So all of this will change to that. And not only that, notice that the one integral, you see here we have one integral, becomes a double integral. And instead of integrating over the curve, what exactly we are going to integrate of, guys? We are going to integrate over the region that is bounded by this closed curve. It's as simple as that. Got it? So no more this. We don't use that if that path is closed. So what do we integrate? Instead of one integral, we use double integral. And what do we integrate over it? Over the base here, which is a region bounded by that path that you take, because the path is closed. So then definitely we have a closed region. Use this closed region to find the work done, period. That's it. This is everything in 912. Let's look at this example. It says, use Green's theorem to find the volume of the solid, or to integrate this one actually. Not the volume, so here I'm just getting carried out with the 911 and 910. Here, he wants to find the work done, because this is P dx plus Q dy. So this is definitely the work done on that triangle. So let's graph the triangle, guys. So I'm going to start with the coordinates. The first point is 0 and 0. This is our first point, 0 and 0. The second one is 0 and 1. That's the second point. And the third one is negative 1 and 1. Here's the third one, guys. So this is negative 1 and 1. And we connect those with a straight line. So you are going to deliver the object. Maybe you can start from here, going all the way up, then this direction, then come back again to your place. What is the work done to do this one, guys? Very simple, because this is a closed curve. So what do? We say the work done is equal to the double integration. You see, I'm going to change the one integral over a curve to double integral over a region of what? dq over dx minus dp over dy, all of this over the area of the region. All right, now the question is, what's p here? P is e to the x squared. We differentiate p partially with respect to y. Notice that there is no y whatsoever, so the derivative is 0. Q is 2 tangent inverse x. What's the partial derivative of q with respect to x? We know that the derivative of tangent inverse is 1 over 1 plus x squared, and there is already 2, so it's 2 over 1 plus x squared. So now we can apply the formula. What's the work done? It's the double integral. dq over dx is this, so it's 2 over 1 plus x squared. It's supposed to be minus dp over dy, but dp over dy is what? Is 0, that's it, so this is what's left. Then what? dA over r. All right, the question is, where is r? R, guys, is our region. Where is the region that we're talking about? This is our region, isn't it? Enclosed by this path. I will take it as a region of type 1. So imagine that we have what? Scanner, the light starts from here all the way to here. Starts from the left. What's this? This is x equal to what? Negative 1. So I'm going to take it as a region of type 1. This is our region. I will take it as a region of type 1. So we say this is double integral of 2 over 1 plus x squared. Then we say dy dx. Alrighty, now what's x here and what's y? Because it's a region of type 1, so x starts from where? From negative 1 all the way to here. What's this? We know this is x equal to 0. So for the x, we're going to start from negative 1 all the way to 0. Now, this light that comes, what's the length of it? Who's the bottom? This one. This one, y equal to what, guys? How do I find it? You see, I have these 2 points, isn't it? Can we find the equation of this line? Yeah. What? It's y equal mx plus b. Any line, this is the equation for any line. Notice that the y-intercept here is 0, isn't it? The line is intersecting at 0. So this is y equal mx. What's m now? So y is equal m. Remember, it's y2 minus y1. So it's 0 minus 1 over x2, which is 0 minus minus 1. So it's 0 plus 1. X, of course, which is going to be negative x. So it's minus 1 over 1, which is negative x. So we have y equal negative x. This is the equation of this line. So on the y-axis, guys, the bottom is y equal minus x. Up to what? Who's the top of the light always? When the scanner comes, this is the top, and this is always y equal what? 1. So here is 1. That's it. This is what you have to do. All you have to do now is to integrate. So we close on the y. And what is this equal to? Integration from negative 1 to 0. Now, what's the integration of that? Remember, this is all constant. I'm integrating with respect to y. So we don't touch this. So this is 2 over 1 plus x squared. Now, what's the integration of dy itself? It's y. From negative x to 1 dx. That's it. Now, what do? We plug the 1 first for y. We get 2 over 1 plus x squared minus, now we put x instead of y, minus and minus becomes plus 2x over 1 plus x squared dx. Now, what's the integration of that? The 2 goes out. What's the integration of this one, by the way? It's easily seen that this is tangent inverse x. Remember that? This is the integration of that one. Plus, how about this one? Look at that denominator. What's the derivative of 1 plus x squared? It's 2x. Is it in the top? Yes. Remember that when you have g at the bottom and g prime on the top, dx, how do you integrate this? What's the answer? It's ln the denominator. So the answer is ln 1 plus x squared. I don't have to put absolute value because 1 plus x squared is positive. Now this is from -1 to 0. Put the 0 first. So this is 2 tangent inverse 0 plus ln. If I put 0 here, I get ln minus. Put now the -1. 2 tangent inverse -1 plus ln. If I put -1 here, you get 1. 1 plus 1 is what? Is a 2. So now, tangent inverse 0 is a 0. Ln 1 is a 0. And what is this? So this is -2. Tangent inverse -1 is minus pi over 4. Because tangent inverse 1 is pi over 4. Plus ln 2. Minus with minus, this goes with that. So it's pi over 2 plus ln 2. This is exactly the work done. And of course, this is all what? In joules. Let's look at this one. Use Green's theorem. Also, you have this closed path. Is this closed path, guys? Where C, take the region out to be ellipse. Here is your ellipse. Look, how is this one ellipse, by the way? You have x is equal a cosine t. And y is equal b sine t. Now look at this now, guys. If I divide it by a, so x over a is cosine t. And here, divide by b. So what do we get from here? Square both, so x squared over a squared plus square this one, x squared over b squared. When I square this one and I square this one, I add them. I'm going to do the same thing here. Square this and square this. So this is sine, sorry. What do you get? You get 1, isn't it? This is an equation of an ellipse. How does the graph look like? It looks like this, guys. We don't know who's bigger than who, doesn't matter. So if we say on the x-axis, here is a and negative a, and here is b, and somehow here, negative b. So the ellipse will look like this. Why is it complete ellipse? Because 0 is from 0 to 2 pi, full rotation. So this is the path that the guy is going to use to deliver the object. It's a closed ellipse. Alrighty, so now since the path is closed, so what do? We do the following. Now what's p here? P is the coefficient of dx, which is -y. So dp over dy is equal -1. Now what's q? Q is the coefficient of dy, which is x. So dq over dx is 1. From these two, dq over dx minus dp over dy is 1 minus 1, which is 2. So according to the Green's theorem, what's the work equal to? Inside, all you have to do is 2 dA over what? Over R. Now, we can take the 2 out I'm left one now with the derivative dA over R. So look what happens here. There is nothing inside, so there is no height. There is only what? Base, isn't it? There is no height at all. The height is 1, so there's no height. And all I have is a base, which is an ellipse. So this is equal to, guys, to what? 2 times the area of the ellipse. You don't have to, there's nothing to integrate here, it's 1. So if I want, I can integrate this one, but why bother myself with doing this? All I'm gonna look is, since there's no height, remember the volume, this is computing the volume, double integral, isn't it? But there is no height, is 1. So what am I doing? I am actually now finding just the area of the base, and the base is an ellipse. We know that the area of the ellipse is always pi times A times B. So the final answer is 2 pi AB. This is exactly the work done, guys. So every time the inside is 1, so instead of finding the volume, what do we find? We find the area of the base, because there is no height now. Let's look at this one. Evaluate this where C is these two paths. It's a region in between, guys. Look at this one. I have a closed region. I have 2 closed paths and I have closed region. So I can do this one over what? Over this closed region. So to integrate this one and find the work done over these 2 paths, if the object is moving here on the outside like this and inside, so this he will be moving what? In opposite direction here. This is going in this way and this is going to this way. And what happens? I have 2 movements here. The region between them is closed. Both paths are closed. So we're going to take the region in between them. So how do we find this one? So if you look at this line, what is this line, by the way? This is the line between, or let's take this line. So y equal what? Mx plus b. What's b here, by the way? Look at this. It's 6, huh? So y equal mx plus 6. Okay, what's the slope? 0 minus 6. Okay, let me do m here. 0 minus 6 over what? 6 minus 0, which is -1. So this is y equal minus x plus 6. This is the equation of this line. All right? So this is the equation of that line. Anyways, what's the distance from here to here? It's the square root of 0 minus 6 squared plus 6 minus 0 squared. And this is equal to the square root. This is 36 plus 36, which is the square root of 6072. All right? So this is the length of that line here. So everything here is the square root of 72. Now let's go to the work done, guys. It's double integration dq over dx minus dp over dy. He wants it over the region A. And this is equal to double integral of. Let's find dq over dx, guys. Q here is the coefficient of dy, which is y squared plus 1. If I want to find dq over dx, notice that there is no x whatsoever, so it's a 0. So this is 0 minus p is cos x squared minus y. Sorry. dp over what now? dy. The derivative of that, there is no y here, so it's a 0. The derivative of minus y is -1. So this is minus 1, and we close dA over R. Minus with minus is plus. So what am I left with? Double integral of dA only over R. So what's going to happen, guys, now? There is nothing inside. So I'm going just not to have a volume, but we're going to have what? An area. Area of the R. Where's R? R is this one, by the way. This is our R. It's the inside thing. This is our R. Everything in here. But what is this? Isn't this, guys, the area of this outside square? You see, this the length here is 6, and this is 6, and this is 6. They're all 6, right? So it's going to be the area of the square of side 6, right? Minus, I will remove what? This area. What is this? This is ellipse, huh? The inner ellipse. But what's the area of the square? Of side what? The side here is, not 6 actually, I'm sorry, the side is square root of 72. Right? This is the side. Square root of 72. This is square root of 72. All right? So I messed up with that one. It's not 6. It's a square root of 72. An area of square of side 72. But what's the area of square root side 72? It's going to be square root of 72 square. This is the area of the square. Minus. Remember, what's the area of the ellipse? It's pi times a. A, look at this. This is minus 2 to 2 in the x, so this is 2. And on the top, what is this? 6. Sorry, this is 4. So this is times 4. B is 4. And this is equal to 72 minus 8 pi. This is exactly the work done in joules. Let's do this question. Find the work done by the force. This is our force function acting along this path. Look at the path. It's a closed path, isn't it? Very nice closed path. So I'm going to do this one. Since the path is closed, we're going to use Green's theorem. To do Green's theorem, what do we say? We say that the work is equal to the double integral of dq over dx. By the way, this is P, and this one is a Q. Now, what's dq over dx? The derivative of this with respect to x is 0. And the derivative of this with respect to x is what? Is 6x. So this is 6x minus. Let's go here to P. We're going to differentiate P with respect to what? To y. What's the derivative of minus 16y with respect to y? It's negative 16, so it's going to be minus 16. Plus, what's the derivative of this with respect to y? It's a 0, so that's it. And dA over R. And this is equal to the double integration of R, 6x plus 16 dA. Now, the inside is not 1, so I can't just take the area of this region, right? So now what do we do, guys? This region can be type 1, type 2, remember, or what? Polar. This one definitely is a polar region. Why is that? Look at this, guys. This one, we're going to start from this. What is this point, by the way? This is the intersection between y equal x, which is this line, and this what? This circle, isn't it? What do you have? You have x squared plus y squared equal 1. Okay, let's replace y with x. So what do we have? So we have x squared plus x squared is equal to 1. So 2x squared is equal to 1. So x squared is equal to half. So x is equal to what? Plus minus 1 over root 2. So x is what? 1 could be plus, could minus. This is the plus 1. This is 1 over root 2. And this one here is minus 1 over what? Root 2. This is the intersection between them. All right, now, but we know that x is equal to what? R cosine theta. And here, x is 1 over root 2, so 1 over root 2 is equal to r. What's the radius, by the way? Look at this. This is a circle of radius 1, isn't it? So what's this length? This is 1, isn't it? The length here is 1. So it's 1 cosine theta. So when is cosine theta equal to 1 over root 2? This is only when theta is equal to pi over 4. So how far is this guy from the x-axis? Is pi over 4. Up to what? Up to here. If you go to the second, y minus x, so what's this? This is a 3 pi over 4. The second ray. To cover the region, remember, from the first ray to the second ray. So this is equal to what? I'm going to use polar coordinates, guys. So this is 16 times x. What's x? X is equal to r cosine theta. Don't put r here as 1. Just leave it r cosine theta. Plus 16. This is not 16, by the way. This is 6. All right. Then what do we have? R dr d theta. Done. Now, what is the length of r? R starts from 0 all the way to what? To 1, isn't it? So r is from 0 to 1. How about theta? It's from pi over 4 up to 3 pi over 4. So if you take this ray and move it from pi over 4 all the way to 3 pi over 4 with length 1, it will cover the whole region. That's it. This is how you set up your integral. Now, what do we integrate with? We'll integrate with dr first, the inside. So this is equal to the integration from pi over 4 to 3 pi over 4. Okay. What's this? I'm going to multiply. So this is the integration from 0 to 1. 6r squared cosine theta plus 16r, all of this dr, then d theta. Now, don't forget we are integrating with respect to r. What's integration of r squared? It's r cubed over 3. And there is a 6, so this is 2r cubed. You see, I'm not going to integrate cosine theta because I'm integrating with respect to r, guys. Plus, what's the integration of this r? R squared over 2. 2 with 16 is 8, so this is 8r. And this is from 0 to 1, then d theta. Now, what do you plug? The 1. So this is equal to the integration from pi over 4 to 3 pi over 4. We're going to replace r with 1 first. So what do we get? We get 2 cosine theta plus 8. Minus, when you put r0, it's gone. So this is what's left, d theta. And now, what's the integration of cosine theta? Sine theta. So this is 2 sine theta plus the integration of 8 is 8 theta. And this is from pi over 4 to 3 pi over 4. And this is equal to 2. We plug the top one. 3 pi over 4 plus 8 times pi over 4. Minus, we put pi over 4 now. So this is a 3 pi over 4. Minus, we put 2 sine pi over 4 plus, and say, of course, there's a minus, minus 8 pi over 4. And this is equal to sine 3 pi over 4, by the way. Pi over 4, sine in the first quadrant is positive, in the second quadrant is positive. So this is 1 over root 2. So this is 2, then 1 over root 2. Now this 4 with this 8 is 2. 2 times the 3 is 6. So this is 6 pi. Minus 2. What's sine pi over 4, by the way? It's same thing. It's 1 over root 2. This one with this one is 2, so you get 2 pi. This guy cancels this guy. 6 pi minus 2 pi is 4 pi joules. This is how much it takes to move the object on this closed path. Last example. You see also this is what? A closed path. Do you see the path here? If you start from here, for example, you go this way, then you go this way, then you continue down, you come back, and then you come back to this point. So this is a closed path. What do we do? We say the work done is equal to the double integration of dq over dx. Here's q, guys. What's the derivative of this with respect to x? The derivative of x is 1. The derivative of y is 0. So it's 1 minus dp over dy. What's the derivative of this? This is p. With respect to y, this is 0. With respect to y, this is negative 1. So it's going to be plus 1 dA over r. And this is 2 goes out, and you have dA over r. Okay, let's look at the region, guys. This is my region. What is this? Isn't this the big circle minus the small circle? What's the radius of the big circle? Look at this circle. The radius here is 2. What's the radius of the big circle? If I make it a complete circle, pi r square, which is 2 square, minus the, remove this inner one, which is pi times 1 square, right? So a big circle minus small circle. This will give us a what? What I just did now is the following, by the way. The big circle minus the small circle will give me this region. This is the area. This is 2, and this is 1. So circle radius 2 minus circle radius 1. But I don't want it all. I just need what? I just need this part, which is 1/4 of that. So this is all divided by what? By 4. This is equal to 4 pi minus pi over 4. And this is a 3 pi over 4. So the answer is 2 times 3 pi over 4. This 2 with 4 is 2. So the answer is a 3 pi over 2. You see how interesting and how easy it is to do it by using Green's theorem. And this is, guys, the end of 912. And this is how we find the work done on an object who's moving on what? On a closed curve. So this is the objective of this section. What's in the next one? Keep it surprised till we go to 913. You guys have a good day.